All right, so we're going to look at section 6.3, which is on graphing sine and cosine. Pretty straightforward. We're going to look at all the shifts, stretches, and flips that we normally do, except we're going to sketch it with a sine or cosine function. So we're not going to do tangent, secant, cosecant, or cotangent this week. Okay. Tomorrow will be a good stopping point for just sine and cosine. We'll look at how to graph tangent and all the other stuff later on, but not yet. So this is the first time that we are going to ever be graphing a function which is called periodic. Right. Let me show you what it looks like first, and then you can probably guess why it's called periodic. Because what's happening is this graph is repeating its values, okay, over and over. Right. So if I go zoom 7, that's the kind of zoom that we use a lot on the calculator. You don't need your calculator for this, but zoom 7 is like a preset zoom for trig. Works pretty good. So if you look, you've got 1, 0, -1, 0, 1, 0, -1, 0, 1. It just keeps repeating those y values over and over. So that's the idea of a periodic function. The same y values just keep repeating over and over. But there's a certain amount of the graph you have to go through before those values will start to repeat. Right, so let's go like this. So let's take a look at this graph. So at the end here, I say that the y values are repeating over a given set of x values. For this graph, here is the width of that set, from here to there. If you focus on what's just in between those two red lines, okay, what I'm tracing in green, that's what we call one section or one cycle of the sine graph. So that from here to here, that's the width of the x values that you have to go through before your graph will start to repeat. Go beyond that width right there, and you're going to get the same values repeating. Go less than that width, and you won't have finished a full cycle yet. Any question on that idea? Okay. So the length of that interval that I have in green from left to right, that's called the period of the graph. You can also call it the length of the cycle. Same thing. Okay, but that's the period. Now, if you just graph what I did here, just a basic sine function. Don't do +2 or ×3. Don't put in any other numbers. Okay? No transformations there. That's has a certain period length. Anyone have a guess how many degrees or how many radians it would take to go from here and to get all the way back where you started? 360. 360. It's kind of like the unit circle. Right? It's 360. Or in radians, 2 pi. So if you don't mess with it at all, the normal cycle length of a sine or cosine function is 2 pi. Now, I didn't graph cosine at the same time, but if I did, you can see they're very similar. What's the difference? If you had to describe it in terms of like a transformation. Yep.
1 unit to the left.
Yeah, it's a translation by 1 tick mark. We don't know how much 1 tick mark is on a trig zoom. It's actually 90 degrees, but each mark there is 90 degrees. So the one in red is actually 1 tick mark to the left of the one in blue, which each tick mark is 90. But other than that, they're the same thing. They're both waves. Okay? The other trig functions, tangent, cotangent, secant, and cosecant, don't look like that. So we're not going to look at those this week. They're very, very different. All right. I already said that to you guys, but another name for a period of the graph is called the cycle. One cycle of the graph. All right, so what I'm going to do, just kind of up front, I'm giving you a bunch of background about sine and cosine. So what they look like, how the graph, kind of the patterns in it and stuff. And then we'll talk about each transformation separately. Horizontal shifts and stretches, vertical shifts and stretches. All right, let's go like this. Now, if I go back to sine. Sine was the graph in blue. That graph has symmetry. In particular, the graph of sine is symmetric over the origin. That's a fancy way of saying that if you did a horizontal reflection followed by a vertical reflection, it would land right on top of itself. So look at the graph in blue. If you mirror imaged it, I don't know, let's go like this. Let's just focus on this single point right there. If you reflected that point horizontally, it would end up right there. If you then reflected it vertically, it would end up right there. So that point ends up down there. That's called symmetric over the origin. Now, if you look at cosine, the one in red, that's a little different. Anyone describe the symmetry for the graph in red? Yep.
Reflection over the y-axis.
Yeah, that's just a reflection over the y-axis. So it has symmetry over the y-axis. This means what it says below it. It's just a way to write it as an equation. If you can take any function in math, not just sine or cosine, but if you take any function and plugging in a negative number or a positive number gives you the same answer, it means that it's a reflection over the y-axis. Think of the graph of y equals x squared. If you plug in 2, what do you get for y?
4.
If you plug in negative 2, what do you get for y?
4.
4. That means a parabola is symmetric over the y-axis, and it is.
Shouldn't it be cosine of negative x equals negative cosine of x?
No, that wouldn't imply this kind of symmetry. No. If that happened, that's what the top one says. So with cosine, this negative, when you're doing arithmetic, it actually doesn't even matter. Like if you had to take the cosine of, let's say, just make up any number, negative 2. But actually type in the number 2. Right, so if you type cosine negative 2, that's what you get. Cosine positive 2, same thing. Doesn't matter. Whether you take a negative or a positive. And that's because of the symmetry over the x-axis, y-axis. Now, with sine, if you take the sine of negative 5, that's what you get. If you take the negative sine of 5, same thing. And that's because of the symmetry over the origin. That's like the double reflection. So with cosine, you can just erase this negative. It doesn't even matter. With sine, you can't erase it, but you can put it in front. And it means the same thing. All right, so it's kind of handy when we do arithmetic. Not something we're going to focus on a ton today, but I do want you guys to notice these graphs have symmetry. Okay? Sine and cosine graphs. All right, so depending on what you're trying to graph, you need a certain amount of points. Like if you need a line, 2 points. It's good. That's all you need. Draw a line right through them. With sine and cosine, we need a little bit more. We've done some graphs where we use the table on the calculator and we get like 8 or 9 points. We're not going to need that many. 5 points is pretty good. Because if we find what are called the 5 quarter points, beginning, quarter of the way through the cycle, halfway through the cycle, 3/4 of the way through the cycle, all the way through the cycle. If we find those quarter points, it will give us all the x-intercepts for the graph. So where it crosses the axis, the highest and the lowest. That's good enough. You can get more points if you need them, but usually we don't. And since these are the quarter points, they're all 90 degrees apart. If you wanted to think in degrees, this point is 0, 90, 180, 270, 360. So the x values that I'm having you pick are not just random x's. They're x's that are nicely spaced every 90 degrees. Okay? Or in radians, 0, pi over 2, pi, 3 pi over 2, 2 pi. They're all nicely spaced.
I'm gonna have to do it to really understand this one.
Yeah, every problem in this section, well, not every problem. Most problems are going to be graphing.
All right.
So when we graph a transformation, you have to know where it starts if you hadn't transformed it. Like you basically have to know where is the original. Because if I say to you, okay, take the sine function and shift it up 2. Well, you can't shift it up 2 unless you knew where it started from. Then if you say, oh, okay, it started at 0 and I'm going up 2, now it's at 2. Or if it started at 1 and it went up 2 units, now it would be at 3. Okay, but you have to know where it starts from. So for every transformation that we do, we're going to use one of the 2 following tables. If it's a sine problem, you're going to use the table on the left. If it's a cosine problem, you're going to use the table on the right. So the x values in these tables are the x values for the quarter points. 0, pi over 2, pi, 3 pi over 2, 2 pi. Any question on what I mean by the quarter points? That seems 0, quarter of the way through, halfway through, 3/4 of the way through, in the end.
So just pi by itself is representative of a quarter.
Pi is 180. That's halfway through the cycle.
Alright.
Mhm.
So then 180 divided by 2 is 90, and then 180, 240, 270.
270 is 3/4, yep. So look at your y values here. This is an actual picture of sine, basically just copied from this screen right here. Look at the one in blue. The one in blue is that picture right there. So when you are, let's make that a little smaller. When you're at 0 on the x, what's your y value for that graph up above?
0 on the x, it's also 0.
Mm-hmm. How about when you're at pi over 2?
You're at
1.
1.
How about when you're at pi?
0.
0. 3 pi over 2?
-1.
-1. And 2 pi?
0.
0. So that's what's in this table right here. Those are the original values. So now if you have to shift left, right, up, down, stretch, flip, you start from those values and go from there. Okay, now let's do cosine. We pick the same x values. Technically, you can pick any x value you want. The domain here is all real numbers. But those are the best x's to pick if you want the quarter points in the cycle. Now, let's look at cosine. Okay, cosine is the one in red. So when we're at 0, what's my y value? 1. And then?
0.
0. -1.
0.
0. 1. And that's exactly the values that are right there. 1, 0, -1, 0, 1. Now, because these graphs go on forever left and right, when you sketch it, you don't have to sketch forever left and right. For every problem, all you have to do is sketch one cycle. That means something like this. That's one cycle. The reason I'm only having you sketch one cycle is because once you sketch one cycle, if you needed a second one, you could just copy and paste that picture again and get a second cycle. You know, forward and backward. You can just keep copying and pasting in the same direction. And if you're wondering, well, how would you do that with the values? You just continue the pattern. 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2. That's 4 pi over 2, technically. 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. You could just continue that pattern and do the same thing in the y's. 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0. You just continue the pattern and you could get more cycles for your graph.
What is the practical implication of this, if there is one?
What's that?
Is there an easy practical implication of this?
Yeah, we can visualize sound frequencies, which is usually I do a demo with all the frequencies and cell phones and different stuff. I think we're going to do that probably one of the days we come back from Christmas break, because it's like a 2-day week. So one of those days would be a good day to just kind of like do this kind of like sound demonstration stuff. Yeah. And then the other day we'll probably do review a little bit for the midterm. We'll start that because it's only a 2-day week, so there's not a lot of time. So we're not going to do much with that week. Okay. So any questions on these tables? Okay, so those are our original tables for the first cycle of sine and the first cycle of cosine. That's all they are. Now, the kind of problems we're going to do today, we're going to do a lot more basic than we normally do. Sometimes I give you a problem and it's got everything in it. It's like shift up, stretch by a factor of 2, flip it, everything. We're just going to do one transformation per problem for today. So what that means is if we shifted up and down, which values are not affected at all when you shift up and down?
The x values.
The x values. So what that means is if we only do one transformation per problem, one column is going to stay the same, the other column is going to change. So either the x's stay the same and you fix the y's, or the y's stay the same and you've got to change your x's. We're not going to have to change the numbers in both columns at the same time today. Tomorrow we'll look at that. All right. So now for the rest of the class to finish up, we're going to just practice each transformation. And there's 4. Shifting left and right, shifting up and down. Stretching left and right, stretching up and down. And we'll do a few of each one. All right, so phase shift. We normally don't call it that when we do other functions, but what this means is horizontal shift. That's what it is. So if you wanted to describe these two graphs, you would say that they are out of phase by 90 degrees. They are out of phase by 90 degrees. So phase shift, horizontal shift, a lot of this stuff you guys are going to already know because this is written for people who've never seen transformations before. All right. So if you already know something, you don't need to write it. What mathematical operation do we have in an equation when we do a shift?
Addition or subtraction.
Addition or subtraction. Addition would move it which way?
Right.
Addition, nope, would not move it right.
Left.
Left.
Or down.
Well, that'd be for a vertical shift. When we get to that, yes. But for a horizontal shift, addition moves it left, subtraction, right. Okay. So, it has the form of addition or subtraction, and the key is it is inside the function. Remember, when you do something inside the function, it's horizontal. Outside the function, vertical. Also, just like we've always done, horizontal stuff is backwards. So positive is left, negative is right. A big number, when we put that in for a stretch, big number actually compresses the graph. Okay, horizontal is always backwards. So we just said this. Okay, so if you know that, you don't need to write it, but if you don't, I would write it. Minus shifts right, plus shift left. It's the same pattern that we've studied with every function we've studied all year. There's no differences at all. I guess the only difference is that now your graph is going to look like a wave. It's not a square root or parabola or anything like that. It's always going to be a wave. Okay, so how do we modify that original table that I gave you? We have to find the 5 points on this graph. Okay, if we do a phase shift, which column is not affected at all? Is not affected. Y's. Phase shift is going to move things left and right. that means y's are the vertical. We're not going to do vertical. We're going to do one thing per problem. So your y's would stay exactly the same. When I say they stay the same, I mean go back to this table and copy down the y values. Which table would you use? Depends. If it's a sine problem, use the table on the left. Cosine problem, table on the right. So the first one we're going to do is going to be a sine problem. Next, you look at your argument. In this case, it's x minus pi over 2. We know that a minus should shift it which way? To the right. The only way you can move x values to the right is if you increase them. That's how x values move to the right. Increase them. So, we have x minus pi over 2. We're going to do the opposite of that. We're going to add pi over 2 to all the x values. And what that's going to do is adding pi over 2 is going to increase them, which is going to move them all to the right. And that's what we want to happen.
So that keeps the same period and the same frequency, it just physically moves the starting point.
Yes, the period is not going to change here. This is a rigid transformation. It just takes exactly what you have and moves it somewhere else. There's no stretch in it. We haven't done that. But yeah, that'll be the last one we do. Okay, so let's make our table. So, first of all, just to explain why it's a period change, subtraction inside the function. That makes it a period change. Makes it a phase shift, sorry. Phase shift. Okay. So, we just said that y's stay the same. What are my y values for sine?
1, 0, negative 1, 0.
That would be if this said cosine.
Oh, that's for cosine?
Yeah.
0, negative 1, 0, 1.
0, 1, 0. What did you say the last two?
Negative 1, 0.
0. Yep. 0, 1, 0, negative 1, 0. Now, the way I grade a problem like this is the table is going to have 10 numbers in it. You get 1 point for each number you get right. So right there, you got 5 points for the y values. Okay. Now, I'm going to put the original x values on the outside. What are my original x values for sine?
0, pi over 2, pi, 3, pi over 2, 2 pi.
2 pi. Now, what do I have to do to all those values?
Take away pi over 2.
Add pi over 2. Right? Because this is supposed to move to the right. The only way it's going to move to the right is if you make all these bigger. So you have to add pi over 2. Add pi over 2, pi over 2. Now, if you need to find common denominators, that's fine. If you can just give me these in your head, that's fine too. All I'm going to look at is what you put in this table. What's 0 plus pi over 2?
Pi over 2.
Yep. Pi over 2 plus pi over 2?
I'll just be pi.
It's 2 pi over 2, which is just pi. How about pi plus pi over 2?
3 pi over 2.
Yep. 3 pi over 2 plus another pi over 2 would be 4 pi over 2, but 2 pi when you reduce. And the last one.
5 pi over 2?
Yep.
How does it go to 5 pi? Oh.
Because that's 4 pi over 2 plus 1 pi over 2.
Common denominator.
Yep. And you should notice a nice pattern. Watch the pattern if I say everything with a denominator of 2. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Perfect. If you had to do another cycle, 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. But that's it. So that's 10 points for that table. Any questions on that?
So if it was adding pi over 2, we would be taking away.
You always do the opposite.
Always
Yep.
do the opposite.
It's the same thing we've done all year. When you see subtraction inside, that moves it to the right, which means x values get bigger. When you see addition inside, it moves to the left. That means x values have to get smaller. So you would subtract. Okay, and now we make our sketch. Okay, for the sketch, we have to label the axis. You can label it any way you want as long as you're consistent. You cannot do something like this. That's not consistent. You were going by ones and then you skipped and now you went by twos and now you're going back by ones. Okay? So we just have to use labels that are equally spaced. Well, remember these values originally. 0, pi over 2, pi, 3 pi over 2, 2 pi. That was 0, 90, 180, 270, 360. Were those equally spaced to start with?
Yeah.
If you take a bunch of things that are equally spaced and shift them all together, are they still equally spaced?
They are.
They are. So you can label your x-axis using the values in the x column. I would label it like 1, 2, 3, 4, 5, 6, because these are awful decimals. Right? We don't even want to think about the decimals. So we're going to call the first one pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2, just like that. Now, on the y-axis, I'm going to go by ones. If you go by ones, you do not have to label the axis. Okay? If you want to go by something other than ones, you do. Okay, so here's your sketch. 0, 1, 0, -1. That's why I moved these labels down a little bit so I didn't have to draw over them. And 0. Here is your sketch. Here's what the original would look like. I'm not going to sketch the original for each one. I just wanted to show you the first time.
Looks like the original slide.
So if I take this one, does this make it red? Red, that's the original. Black is the transformation. That's the new one. So it's been shifted to the right. How much? Pi over 2, which is 90 degrees. Okay. Any question on that? In terms of transformations, I think this one is the hardest arithmetic-wise. They get easier from here.
That's good.
So if you get this one, then you're probably pretty good for all of them. Okay, let's look at this one. All right, so how do we know what kind of transformation it is here? Zach?
Since it's a plus, it's going to be to the left.
So it's a plus, and where is it?
It's in the parentheses.
It's inside. Addition inside means phase shift. And Zach just told us which way it's going to go. It's going to go to the left. So, since it's going to move to the left, which column is not affected?
The y's again.
The y's. And now my y's for cosine.
1, 0, -1, 0, 1.
Yeah, I think that's what we had said earlier when we were doing the sine problem on accident. So that's good. Now your x's. 2 pi. I'm going to put all our answers right here. Okay. What am I going to do to all those x values?
Minus pi.
We're going to minus pi. So, minus pi, minus pi. Okay, some of them are quick. 0 minus pi, pi minus pi, 2 pi minus pi. How about pi over 2 minus pi?
2. 1 pi. Pi over 2.
Negative pi.
Negative pi over 2, yep. How about 3 pi over 2 minus pi?
Pi over 2.
Yep, pi over 2. And if you look at it in degrees, you get a nice pattern. -180, -90, 0, 90, 180. They're all 90 apart. Perfect. And that's your table.
Do we ever have to graph that? Or are we
Yeah.
just going to ask this for tables?
Yep, just like we did in the last one.
Well, like in the calculator.
No calculators at all. In fact, for this test, yeah, you won't need one at all.
And this is a take home time testing.
Yep. So negative pi over 2. I should probably write those lower. They're too high. 0, you don't have to label unless you want. That's the axis. Pi over 2. And pi. Let's move those. Good enough. Okay, again, I'm going to go by ones on the y-axis. So no labels needed. So 1, 0 is my y-intercept. Pi over 2, 0. Pi, 1. Now, it looks kind of like a V, but remember, it's like the middle part of the wave, that's all. So try to make it look a little bit curved. Like that. And what actually happens right here and right here, those are called inflection points. The graph goes from being what we call concave up. You can think of concave up as holding water to concave down, which water would now fall out of. And that happens right at these 2 points. Goes from concave up to concave down.
So the most you're going to ask for like a single question is 1 period of the graph.
Yep, 1 period, 1 cycle. Same
and
thing.
with all the points listed.
With all the points, yeah. Yep. Because now if you wanted a second cycle, just continue this pattern forwards or backwards, and you can get another cycle if you need it. All right, let's do one more, and then we'll be done with phase shifts. Okay, so that's addition. Which way is this graph going to move?
Left.
Left. Y stay the same. So my originals are 0, pi over 2, pi, 3 pi over 2, 2 pi. And what are we going to do to all those values?
Subtract 4 pi, or pi over 4.
Subtract pi over 4 from all of them. Again, no decimals here. Just leave everything as fractions. First one's not bad. What's 0 minus pi over 4?
Negative pi over 4.
Yep. Now, for the second one, if you needed a common denominator, think of it as 2 pi over 4 minus 1 pi over 4. How much is that?
Pi over 4.
Pi over 4. Now, the gap that you have between the first two has to be the same gap all the way through. So what would the next one be?
Pi over 4. No. I was looking at pi over 4.
Yep, 3 pi over 4. And the next one?
Pi over 2?
Pi over 2. No.
That's reduce. No, wait.
Negative pi
Pi.
over
6 pi over 4, take away 1 pi over 4. 5 pi over 4.
Oh, yeah.
pi over 4. Probably multiply the 2 over.
Just double the top, double the bottom. And the last one?
7 pi over 4.
7 pi over 4. Now, look at the numbers in front of pi. Just the number in front of pi each time. What's the number in front of pi in the first one? Then?
4.
Yeah?
3. 5. 7.
All right. Let's pretend you wanted to put those numbers on a number line. However you put those on a number line is exactly the same way you'd put those on a number line. So here's your number line. I'm going to mark 0. Where would negative 1 go?
1 left.
Yeah, 1 to the left. Where would 1 go?
1 to the right.
1 to the right. Now, where would 3 go?
3 to the right.
Why not right next to it? Everything else was right next to each other.
It's not even.
Right. You have to skip. And if that seems confusing, then I think if you look at it that way, it should make more sense. You have to skip. So 0 was here, you skipped it. 5 and 7. So you end up skipping every other line. Okay? Anytime that 0 is in your list, you don't have to skip. Now, you might look at this one and say, yeah, 0 is not in this list. Why didn't you skip? That's because 0 would be the next one up. This is 5 pi over 2, 4 pi over 2, 3 pi over 2, 2 pi over 2, 1 pi over 2, 0 pi over 2 is in the list. It's just not in the part of the list that we wrote. Okay, so 0 is in that list. Here, 0 is never in this list. Here's negative, here's positive. There's nothing in between. You skipped right over 0. So, when you label your axes, this is how you do it. Negative pi over 4, you're skipping over 0, and here's pi over 4. Here's your gap. That's negative pi over 4 to pi over 4. That has to be the gap each time. So your next label goes here, here, and I think I need one more. 7 pi over 4. That's the only thing tricky that can happen with a phase shift, is numbering your axes. You'll know if you number it wrong, because when you go to draw it, you'll probably get something that looks like this. It's like really squished in one part and then kind of stretched in the other. So you'll know. Okay, so now we're at 0, pi over 4, 1, 3 pi over 4, 0, negative 1, back to 0. And that looks, it's a little bit off, but that's not bad. Okay, any questions on that one? So that's the most annoying one, I think, for what we really do today. All right, so that's our horizontal shift. Vertical shift. What operation is involved when you shift up and down?
Plus and minus.
Plus or minus? Where is it?
Outside parentheses.
Outside parentheses. So a vertical shift, again, this is written for somebody that's never seen transformations before. It shifts the graph up or down. It's when you do plus or minus on the end of the function, or outside the parentheses. Now I did D because when we do all the transformations tomorrow, there's 4. D is the last one. Vertical shift is the very last thing you would do when you have to do multiple in the same problem. Okay, but we've gone over that order at least 6 or 7 times. But we'll do it again tomorrow. What happens if you add outside? Which way does your graph move?
Up.
Subtract outside?
Down.
Down. You don't do the opposite. Vertically, what you see is what you do. Plus is up, minus is down. Now, we got to think about getting those 5 points from our table. Which column is unaffected this time?
X.
X's. And it's nice when the X's, we don't have to mess with them because the X's are a pain. They have all the fractions with all the pi's in them. You don't have to touch them this time. So your X's for every problem that we do in this part of the lesson are 0, pi over 2, pi, 3 pi over 2, 2 pi. Don't touch them. Leave them the same. Okay. So, as I just said, copy your X's down from the original table. And for your Y's, super easy. All you have to do is add or subtract whatever the number is at the end to the original Y values. If it's plus D, add it. If it's minus, subtract. And that's it. So all you're going to have to do in this step is arithmetic with a 1, a 0, or a negative 1. Very, very, very easy. Okay, I'll probably do one graph in this section. If you need to see the other one, we can. But I think one will be sufficient. Okay. What kind of transformation is this out of the 2 we've studied so far? Yep.
It's a vertical shift up.
Why?
Why? Because it's plus 2 outside of parentheses.
It's plus, it's outside. That's the 2 things that make it a vertical shift. Plus, outside. Okay. So which column stays exactly the same?
X.
X. What are my X's?
0. pi over 2.
Pi.
3 pi over 2.
Yep.
2 pi.
2 pi.
There's two of them.
So we got my x's. What are my original y's for cosine? If you can do this in your head, that's fine, but let's just write the originals first.
1, 0, -1, 0, 1.
And what are we going to do to all of them?
Add two.
Add 2. So 3, 2, 1, 2, 3. Done. Very, very simple arithmetic.
This time is easy.
That's pretty cool looking.
So 3, 2, 1, 2, 3. All right. Now let's do our graph. I've got 0, 1, 2, 3. Technically, I don't need to put those labels because I am just going by ones on the y-axis, but I did. And now my x's. Do I need labels?
Yeah.
Yes. If you don't put labels, I'm going to assume this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 are not the numbers in your table at all.
That's like 6.
Yeah, it goes up to like 6.28, so we don't want to deal with that. So 0, 1, 2, 3, 4, 5. And now plot your points. 3, 2, 1, 2, 3. Okay, on the test and the homework, I've got graphs already printed, and it's got dots on it, so it's very easy to plot. For me, it's hard because I'm close to the board. But there's your sketch. Any question on that one? Okay, this one, we don't have to sketch it. After we do the table, if you feel we need to, we can, but I think you guys could do it. What kind of transformation?
Vertical shift.
Yep.
Down.
Down how many? 3. So, x's, 0, pi over 2, pi, 3 pi over 2, 2 pi. What are my original y's for sine?
0,
Oh, sine.
-1. No.
0, 1, 0, -1, 0.
And now minus 3 from all of them. For the first one,
-3, -2, -3, -4, -3.
that's it. And now you just make your sketch. Any question on how you do the sketch? Okay. So there's your second one. There's your vertical shift. So now we've done all the shifting. Let's finish up with the stretches. All right. So first stretch we're going to look at is a vertical stretch. So a vertical stretch is going to affect what we call the amplitude, okay, or the height of a sine or a cosine wave. So the amplitude is the distance measured from the center of the wave to the top, which should be symmetrical from the center of the wave to the bottom. Now, since amplitude is a height, what kind of number do you think amplitude always has to be?
Positive.
It has to be positive. I said to you most of the questions in this lesson will be graphic. This is going to be the first time I give you a question that's not going to be graphic. I'm going to ask for a number for the answer. We are going to do a graph of this too, but I'm going to show you one other type of question I could ask. So, amplitude. Amplitude change. Again, if you want to think of that in terms of the words we're used to using, vertical stretch. Any kind of stretch is when you multiply. Okay? Shifting is when you add or subtract. Stretching, multiply. Vertical, outside the function. So, 3 sine x, 2 sine x, -5 sine x. Those are all vertical stretches. The negative also causes something else to happen. Does anyone remember what a negative does with this? A vertical flip or vertical reflection. Yep. So, this is where I can ask you a question. What is the amplitude? So, we're going to do a question like this in a second. Find the amplitude. No sketch. I just want to know a single number is the answer. So the number that I'm going to be looking for is the absolute value of what's in front. Okay. So amplitude change is going to stretch or compress the graph vertically. Taller, shorter. So let's find the amplitude. What's the amplitude of that graph?
3.
3. How about the amplitude of that one?
4/3.
4/3. Don't be confused because there's a vertical shift and a phase shift in there. Those are separate. Those do not matter for amplitude. What's the amplitude of this one?
-2.
2. What's the amplitude of it now?
2.
Still 2. That negative does not cause a change in the amplitude, but would it change the graph when we do it?
Yes.
Yeah.
Yes, it would flip it. Okay. Flipping it doesn't change the amplitude, but it changes the picture. Okay. So any question on that one? So on the test, you'll probably have maybe 1 or 2 questions like this. Non-graphic, just find the amplitude. That's it. All right, now we'll do a graph. So when we do an amplitude change, which values are not affected?
X.
The x. We are stretching along the y-axis. So that's great. X's aren't affected. That means I don't have to mess with any of the fractions with pi. So copy the x's down from the original table. Now, to find the new y values, take the number that's in front. Do not use the absolute value of it. Because if there's a negative, that's important. That changes the graph. So take the value that's in front and multiply all the old y values by the number in front. If it's positive, use it as a positive. If it's negative, use it as a negative. I think this one and vertical shifts are the 2 easiest in terms of arithmetic. I think the first one we did is a little bit harder. I think the last one we're going to do is kind of the same as the first one in terms of difficulty. Okay, so first thing we'd have to do on the test is identify what kind of transformation it is. What is this one?
Vertical stretch.
Vertical stretch. Why?
Because the 3 is in front of the cosine out.
All right, so it's
being
outside.
multiplied outside the function.
Exactly. 2 keywords there. Multiply, outside. Multiply means stretch. Outside means vertical. Okay. So, which column stays the same? X. And what are my x's?
0, pi over 2, pi, 3 pi over 2, and 2 pi.
2 pi. Now, you might not need it, but I would put your originals just on the outside, so you don't forget what those are. And what are we going to do with all of them?
Multiply them by 3.
Yep. And what would they be?
3, 0, -3, 0, 3.
Perfect. So there's your table. 1 point for each x, 1 point for each y. Right. Let's do our sketch. Now, one thing you might notice is that all my vertical stretches are going to look the same. That's because I'm going to change the scale. Because if I had to graph something that was like 30 cosine x, I don't want to have a piece of graph paper that's 30 times as big. So all I do is this. Change the scale on your y-axis now to go by 3s. X-axis I'm going to keep the same. Pi over 2, pi, 2 pi over 2, 2 pi. Any question on that idea of changing the scale? It's pretty straightforward. Okay, so there's your y-intercept. There's an x-intercept. That's the lowest point that the graph is going to hit. Another x-intercept. And the highest point that the graph hits, which is the end of the first cycle and the beginning of the next. If it's a little off, it's okay. Make your sketch. And does anyone remember what I said this point was called? That's where it went from concave up to concave down.
Water cup.
I know, I remember water cup and concave.
Inflection. Point of inflection.
Would you call it an x-axis? Or like
The x-intercept is a point of inflection here. Points of inflection can be anywhere in a graph. You'll learn that in calc. But these happen to be on the axis. Yeah. Okay, there's your sketch. Questions on that one? All right. Let's look at this one. I'm not going to sketch this one unless we need to. What are my x values here?
crazy.
0 pi over 2 pi, 3 pi over 2, and 2 pi.
2 pi. And now let's see if we can do the y's without writing the originals first. So what are my y's going to be?
So
0.
0, a half,
Yeah.
0, negative a half, 0.
Perfect. Here's your y's. Any questions on how you'd sketch that? Let's do, I'll do one more of those. Now, what's the amplitude of that one?
1.
1. So technically it's not an amplitude change, but it kind of falls in the same category because you are multiplying by a number in front. What's the number? -1. So the 1 part isn't really changing the amplitude, but the negative part is doing a what?
Flip.
It's doing a flip. So x's 0, pi over 2, pi, 3 pi over 2, 2 pi. And now your 1s would have been 1, 0, -1, 0, 1, but the sign is going to change for all of them. And that's going to cause a flip. So -1, 0, 1, 0, -1.
Ooh.
So instead of being like the normal part we sketch is like a valley, this part is going to be like the hill in the wave. So we've got, let's just put these here, pi over 2 pi, 3 pi over 2, 2 pi. Alright, so we got our y-intercept, x-intercept, highest, another x-intercept, and the lowest kind of in a bad spot. It's okay. So it's going to look like this. And remember, it would continue. You don't have to draw the dotted part, but that's how it would keep going. All right, any question on that one? Okay, so we've done both the shifts. We've done the vertical stretch. Last one we will do is the horizontal stretch. But one question first. What's the amplitude here? I didn't ask that.
1/2.
Yeah. What if I did this?
1/2.
Still 1/2. Okay. So, period change. Again, for some reason with trig functions, they give a special name to each transformation. They call horizontal stretches period changes. Now, what did I say earlier that the normal cycle length was if you don't mess with it at all?
360.
360 or 2 pi. We haven't messed with that yet. We've shifted left and right, we've shifted up and down, we've stretched up and down. That hasn't changed the cycle. So the standard period is 2 pi. Now, a period change, or a horizontal stretch, is when you multiply, but it's when you multiply inside. So now this is the opposite of what we would expect, because it's inside. If I put in a big number for b, what's that going to do to my graph?
Squishy.
It's actually going to compress it,
Like a spring.
right? Yeah, it's going to compress it smaller. If I put in a small number for b, like 1/5, 1/6, 1/2, it's going to stretch it. The smaller the number, the more stretch you get. So, we're only going to look at examples where b is positive. We could look at ones where b is negative, we're just not going to. If b was negative, it would be a flip. Okay? We're just going to stick with positives. So period change, stretches or compresses the graph along the x-axis. So if you had a graph like, let's do sine x and sine 5x. Is that 5 going to compress or stretch? It's going to compress. In fact, what's going to happen is it's going to compress it 5 times as much. So for every 1 cycle of the graph in blue, you're going to see 5 cycles of the graph in red in the same space. Because it's been compressed by a factor of 5. You could count it, but there are 5 cycles per 1 cycle of the one in blue.
That does look like a weird frequency.
Okay. Any question on that? All right. So this is kind of like vertical stretch because I can ask you a non-graphing question. What I can do is ask you, okay, we knew the period was 2 pi. You changed it. What did you change it to? Well, to figure that out, you use this formula. T equals 2 pi divided by b. That's how you find the period when you change it. So like in this problem, the period of the graph in red is 2 pi over 5. It's 1/5 as big as the original. Okay. So let's try this one. What would be the period of sine 2x?
Equals 2 pi over 2.
Could be pi.
Which is just pi. Is that a smaller period or a bigger period than the original? Smaller. It's half as big. The normal was 2 pi. This is 1 pi. So you compressed it. You made the period smaller. How about this one? What would be the period there?
2 pi over 3. Wait.
6 pi.
You're so smart.
2 pi divided by 1/3. 2 divided by 1/3 is 6. Think about 1/3. That's a small number. The graph should get bigger, and it did. The period got 3 times as big as it normally should be. How about this one?
Pi
squared.
2 pi squared.
Wait, no, it's 1 over pi.
The formula is 2 pi
Oh, it's
divided
2.
by b.
It's 2.
It's 2.
2.
So this one actually, if you were to graph it, would work out very nice with the quarter points. 0, half, 1, 1.5, 2. So you'd have very, very nice points here. When you have pi, it's not nice. How about the period here?
Oh god.
3.
Oh, that would be.
So it would be
That's
1
just
2
pi.
pi over
That would.
3.
Pi.
2 pi over 3.
Yeah.
So 1 pi.
Well, it's 2/3 pi, not 3 over 2, 2 over 3. 1.5 is 3 over 2.
Yeah,
So
sorry.
don't worry about this plus 2. That's shifting up 2. That doesn't matter. Don't worry about this vertical stretch. That doesn't matter. 3 is the only number that matters.
Okay.
Okay? So,
Like number.
well, when you're talking about what is the period. Yeah.
Okay. But if we were just doing that, then those do matter as well.
Yes. So now, period change stretches or compresses the graph. Which way? Horizontally. Horizontally changes which values?
X.
X's. So the X's are going to change. We don't like when the X's change because that means we have to work with those values that are lousy. Okay? The X's are going to change. That means the Y's stay the same. So at least we got something staying the same. Now, to find your new X values, just take the old ones and divide by B. Why divide? Because the original problem had multiply. And we always do the opposite for horizontal stuff. That's why we're going to divide.
What is that W symbol you've had before? Is that like?
That's omega.
Okay.
I crossed it out because in the trig book I use, they use that Greek letter to represent what I use the letter B for. I like using B because I think if I used B, you'll remember that it's the second thing you would do.
Oh, okay.
That's why if you noticed in the transformations today, I used the letters A, B, C, D.
Makes sense.
So I gave you the order you do them in automatically.
Thank you.
Yep.
I didn't.
Even though today you don't have to know the order because I'm only giving you one transformation per problem. But tomorrow we will.
Oh.
A was the very first one we did. That was phase shift.
So horizontal shift.
B was the horizontal stretch. C was the vertical stretch. D was the vertical shift. Okay. So let's finish up and we'll just grab a couple of these. Okay, now we know all the transformations. Which one is that?
Horizontal stretch.
Why is it a horizontal? Why is it a stretch?
Because it is inside the function and it is being multiplied.
Exactly. Multiply
By the
inside.
variable.
Yep, multiply inside. So, y's are going to stay the same. What are my y's for sine?
0, 1, 0, negative 1, 0.
Okay, now the x's, 0, pi over 2, pi, 3 pi over 2, 2 pi. Now, you can think about doing this two different ways. This is fine. Take all the original x values and divide by b. What's b in this case? It's a half. So, dividing each one of these by a half, kind of weird to think about. It's the same as what?
Multiplying by
It's the same as just multiplying by 2. So let's think of it that way.
So
Times 2?
0, pi, 2 pi, 3 pi, 4 pi.
Yep.
Oh, that's so clean.
Yeah. Sometimes they come out nice like that. Sometimes they're a little messier, but that's the idea. Okay. Now label your axis and we'll go from there. So pi, 2 pi, 3 pi, 4 pi. Not going to worry about the y's because I'm going to go by ones. 0, 1, 0. It's okay. And back to 0. Now, that doesn't really look stretched or compressed at all. Looks just like all the other ones I've done. How come?
Because you changed your x
I changed my,
value.
yeah, I changed my scale. Right. It is stretched out by a factor of 2, but I made all my x's twice as big as well. So I didn't need a bigger graph. So it looks the same. Yep. The original would actually be right here. It's not perfect, but that's what the original would look like. And that's the new one. Okay, let's do this one. Okay, what column stays the same?
Whoa.
The y is no, the y is
No, it's still y.
And what are they?
is negative 1.
No, it's 1, 0, negative 1, 0, 1.
Now we're going to take all of these and divide them by what?
A half.
2.
2.
Yeah, by 2 and then multiply it.
Or you can think of it as multiplying by a half. This time I think whichever one is easier for you.
So 0,
Yep.
pi over 4, pi over 2, 3 pi over 4,
And
2
Pi.
pi.
Now if you look,
It's just pi.
you might say, ew, they don't look like there's a pattern, but there is. That's 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So there is a nice pattern, but you don't see it if you reduce. But you should reduce.
This is gross.
It's gross.
Why? There's pi.
Yeah, it's pi.
This is gross.
Does anybody need to see the graph on that one?
no,
No.
it's just going to.
It's gonna look the same. It's just gonna have 0 pi over 4,
Yeah.
pi over 2, 3 pi over 4 pi, and you're gonna draw a V shape.
Yeah.
But and if you drew the other one, it would be longer. So
Um,
this is a compression.
this is a compression. Yeah, it's been squished. It's been squished. Yeah.
Alright.
Now, last one. When we look at that one, you might think, well, geez, we're already starting with a number in front of x that's awful. The numbers are just going to get worse. Actually, the numbers here are going to be the nicest numbers we've had yet on the table.
Yeah, because pi is going
The pi's are going to cancel. Watch what happens.
it's going to be added to cookie.
So those stay the same. Now you've got 0, pi over 2, pi, 3 pi over 2, 2 pi. Now, we're going to divide all of those by what?
Pi over 3.
Yep, divide them by pi over 3, or
Multiply by 3 over pi.
that's the better way to think about it here. Multiply everything by 3 over pi. Well, that stays the same.
So
3
halves.
times
So that's 1.5 times 3 over pi,
3.
3. And now if you see the gap, it's 1.5.
4.5.
So 4.5
6.
and 6.
Whoa, that's so nice.
So now when you sketch this one, if you wanted, you don't have to label anything. 0, 1, 1.5, 0, 3, negative 1, 4.5, 0, 6, 1.
Oh my lord.
That's something.
That's amazing.
That's
Wow.
Okay? So homework tonight, it's going to be a worksheet. I accidentally
Twice.
copied one page twice. I meant to put in, I gave you the same transformations twice, so I have to give you guys one page separate.
Wait.
And I'm going to have you cross out the page I copied twice. Literally the same problems in the packet twice. So I'll have you cross out the duplicate.
wait. You're giving a packet?
Yes.
That's what I'm
I
saying.
mean, I would rather have the packet than the book. To be
Yeah,
That's what I'm saying.
You've never done a non-book thing.
Yeah, well,
We have a couple weeks coming up in Trig that I like a different book better, so I'm actually going to give you a packet for those weeks
What
too.
book is it?
We're going to do, it's called Unit Circle Trig. It's the book I use in my CP4 Trig class.
So it's called Unit Circle.
It's called Unit Circle Trig by Michael Sullivan, I think. 7th edition.
7.
7th.
That's
Seven.
So I'm gonna give you guys a packet for that week too.
You're right.
I would rather have a packet than the book.
I